This is lecture number 20 of the course AU 203 Statistics and Quality Control. We have already done normal distribution. Today we will explore it further and we'll go into this so-called standard normal distribution. First we will go into the concept behind standard normal distribution. Why do we need that? Why normal distribution is called as standard normal distribution? And then we will look into the tables through which we can calculate the probability of a normal distribution, and then in the end we will go into the normal approximation to binomial distribution, and we will see that how this approximation can be improved through continuity correction. Okay, so as we have learned that in normal distribution there are two parameters involved, mean and standard deviation. So if we have to draw the shape of the distribution for every value of mean and the standard deviation, there will be a particular curve, and the area under the curve is representing the corresponding probability. So theoretically we could have infinite number of shapes for normal distribution. So and each shape would be differing when the value of the mean and standard deviation is different. So for every value of mean and standard deviation there will be one distribution. Let's say if we have a particular normal distribution in which let's say we have two distribution 1 and 2, and the means are different. So the first distribution having a mean of 50 and the second distribution is having a mean of 60. So 10 units, the second distribution is 10 units offset with the first distributions, but shape of the distribution is decided by the standard deviation of these distributions. Since the standard deviation of this distribution is identical, so shape would be identical. Only thing that has changed is the different mean, and so one can say that the mean is actually representing the location of the distribution. Let's say if we have a normal distribution with the same value of mean but have different standard deviations or variances. So let's say for example here the first distribution having small variance, second one is slightly higher dispersion, and third one is having the maximum having higher than 1 and 2, higher distribution than 1 and 2. So here the value of mu is fixed for all three distributions, but the shape of the distribution is determined by the corresponding standard deviation of that. So what we need is we could have infinite number of shapes of those distributions would occur depending upon the value of a mean and standard deviation. So what we need is we need to get rid of this difficulty, and we call that thing to be standardization, which transform that different normal distribution curves into a one normal distribution curve, and that particular distribution curve we call it an standard normal distribution curve. So instead of, let's say we have x is a normal random variable with the mean value would be equal to mu and variance is sigma square. What we do is we standardize by transforming the random variable from x into another random variable named z. So z is representing another random variable which can be calculated if we have a knowledge of x random variable. If we subtract it with its expected value and divide by the standard deviation, so the new variable generated would be standard normal variable. And if you look at its parameters, if the value of x is equal to z, it means that here once you put x and z are identical, so the expected value of z would be 0 and its variance would be unity. So square of 1 would also be 1. In this way, we will be able to transform the x variable into z variable. And the shorter notation for writing down this so we see here, let's say if you have a situation in which your mean value becomes 0. So mu is 0, let's say, and your standard deviation is unity 1. Then x would transform into z. Then the value of x would be the same as the value of z. So we can say that when your mean is 0 and your variance is 1, then the normal random variable x transformed into another random variable z. And so we can say that z is a standard normal random variable, and that represent a standard normal distribution. And but this distribution have fixed value of mean and the variance. So it means area under the curve would be a fixed value. So by doing this transformation, mathematical transformation, where x is transformed into z, we will be able to turn our random variable into a standard normal random variable. And here z is a standard normal variable with the mean value equal to 0 and variance equal to 1. If we just take an example, we have earlier in the previous lecture that this green distribution having a mean value of -2 and the variance is 1. So if the red distribution is the mean value is 3 and the variance is compared with 1, it is half the standard deviation. So it means there is a less dispersion. Let's say if we have a distribution with mean value 9 and the variance is much bigger than the first distribution, that is in the green. So we have 3 different distributions, and each distribution is represented by a random variable, and their parameters are mean and the standard deviation, mean and the variance actually. So what we do is we transform that each and every each of those distribution into a variable called z. So once we transformed it into variable, let's say z would be, in that case, would be x minus, and its mean value is -2 and its variance is 1, so it would be x plus 2 upon 1. And if we transform this red distribution, its random variable would be x and its mean value is 3 and its standard deviation is 1 upon 2. And if we transform this third one where mean is 9 and the standard deviation is 2, so we have transformed all these different distributions into different values of z. And one thing that is crucial about the z is such a distribution whose variance and mean is a fixed values. Mean is always a 0 value and the variance is 1. So all these distributions, different normal distributions, have transformed into a single distribution, and that distribution has been given a name called standard normal distribution. And so let's say we have a normal distribution with mean and standard deviation, mean and let's say the area and the probability between the limits a and b represented by this area under the curve. Once we transform this x variable into z variable, then the transformation would be x minus mu over sigma. And this distribution would turn into a particular distribution with the random variable z, whose mean will be 0 and variance would be 1. So essentially, just because of this mathematical transformation, the corresponding probability between the limits a and b remains the same. So here, after transformation, x is a here, So it would be A minus mu over sigma, and if it is x is B, then B minus mu over sigma. So these would be the corresponding value of z corresponding to the limit A and B. But in both distributions, area under the curve remains the same because they are representing the same probability. So what we do is by transforming z x into z, we can say that x would be equal to just multiplying z with the sigma and adding the mean. We will be able to convert into a variable x. So here mean is actually called as a location parameter, which would be any real number, and sigma would be a standard deviation called a shape parameter or scale parameter, because different values of sigma is representing different shapes for a given value, given mean value. So all these this transformation turns the normal distributed random variable x into a standard normal variable, and we can see that the area under the curve would be a fixed value, because here the mean for z is 0 and its variance is unity. We used to have different tables which actually gives the area under the curve of this standard normal distribution, and how we can recognize the standard normal distribution is that its mean is always 0 and variance is 1. So we have that if you see the PDF which is 1 upon under root 2 pi and sigma is 1. So we have transformed standard normal variable into standard normal variable, and similarly here this u can be called as a dummy variable, because here x minus mu, so x mu becomes 0 and sigma becomes 1, so it would be just minus 1 upon 2 u square. Since as we have already seen that why we do need to have this dummy variable, because in the limits of an integration, which should be ideally go from minus infinity to plus infinity, then the area under the curve must be equal to 1. But what we are doing is we are not going up to the limit 1 from minus infinity, but we are going from minus infinity to some value of small z, which is exactly the same thing as small x. Small x is the value of a random variable capital X. Similarly, the small z is representing the value of a transformed standardized normal variable. So for that particular value, if it is random variable have a probability less than to some threshold small z, then the area under the curve would be from minus infinity to some value of z. And since once you integrate and you put the limit, so finally your answer would be in terms of z. And that is represented by the area is represented by this function phi of z. So phi of z is nothing, just representing the area under the curve, which will be representing the some probability for a value less than z. As you know, z can start from minus infinity, so as you know, value of z would be minus 3.9 and going to minus in this table, and if we continue this table, then we will end up the value of 0, and then the value of z would be greater than 0. So here in this table we can see that the value of z is from 0 to some positive value. So at 0 you can see that the area under the curve is exactly 0.5. It means the area under the curve for this whole distribution is the sum must be equal to 1. So at 0 the area would be 0.5. So once we do its cumulative, it means for this given value of z, let's say for value of z is 1, so its area would be 0.84134. So from 0.5 plus some area if you add them together, it becomes 84% area at the value of z equal to 1. So and the maximum value obviously in this table would go up to exactly the same as 3.9 or 3.3 value, approximately towards a little higher than 3 value, just like the previous value was minus 3.9. So maximum value in the table would go to up to plus 3.9. Okay, even if some of the tables value is given not in the negative value, only in the positive value. So if it is in the positive value, it means it is representing half of the area, and the half area is 0.5. So since it's a cumulative standard normal distribution table, it covers the area under the curve from the value less than some threshold value z. So whenever your random variable z would be less than some a particular value of z, which is represented by small z. Okay, now let's say the same problem we have done using the mini tab, because the issue in normal distribution was that the shape of the curve or the area under the curve for that particular function would be for each distribution having a different value of mean and standard deviation, there would be a different area under the curve. But for standard normal distributions, since mean and variance is fixed, so area under the curve would be remain the same. So that is an advantage where we can use standard normal distribution to calculate the probability for a given distribution. So what is the idea? Once we have to do it using the table, we have to transform the x variable into a z variable. The same problem, the first step is always we have to identify a random variable. Continuous x is a continuous random variable, which is actually representing the height of the adult American female from the population, and from the data we know that x is a random variable which is normally distributed with mean value is 162.6 and 6.8, and we have to calculate that the probability of a random variable should be greater than 170.5 centimeter height. So what we do is, the first step is since we are using a manual or table to calculate probability instead of software, so we have to convert this variable x into a standard normal variable z, and the formula for calculating the z would be x minus mu over sigma. So as I know, the value of x here is 170.5 and its mean value is 162.2 and its standard deviation is 6.8. So I have transformed the value of x 170.5 into z value, which comes out to be 1.22. So if my x value is the same as the mean, then I am always going to get the z value 0. So and sigma would be 1, because that is actually converting it. So what actually have done is, by transforming x variable into z variable, which is a standard normal random variable, which is normal distribution obviously with mean value 0 and standard deviation 1. So what I do is, I need to calculate the value of z greater than 1.22, because 1.22 is corresponding to 170.5. So greater than 1.22 means 1 minus probability of z less than 1.22, because our table is always talking about cumulative value of z, which is always less than to some threshold value of which is represented by small z. So here small z is 1.2 and the second digit is 1.22. So corresponding to this row 1.2 and 0.02, so my value would be 1.22. So corresponding to 1.22, the area under the curve is 888767. So that would be the corresponding probability for z less than 1.22 would be 0.88677. So once I just substitute 1 minus 0.87, so I will be able to calculate the probability of z would be 0.11223. So we can do it in the mini tab also, where we choose the standard normal variable as mean is 0 and the variance is 1, and we substitute the value of z in a constant value would be 1.2. So greater than 1.222 I'm going to get the area under the curve would be 0.1112. So this is exactly, there is some round off depending upon the number of digits available in the table. So this is how we need to solve problems in exam, because you don't have a mini tab available. So you need to convert a variable x into variable z, and to calculate the probability using the table, cumulative standard normal distribution table, and then we will be able to calculate the value of x. So for this particular problem, the probability would be this one. Okay, another problem in which the height of the adult female, which is approximately normally distributed with the same problem, but here the problem is given in reverse, where the 90th percentile, what is the 90th percentile of the height of the adult American female. So here random variable once again is x, and the distribution is normally distributed. So what actually in the problem it is given as the 90th percentile. What is the 90th percentile of the height? So it means I don't know what will be the value of random variable x, but it should be some value of some threshold where area under the curve is covering the 90% area. So what is 90th percentile would be of the height means for that particular value of a, where area under the curve is 90%. So it becomes a reverse problem. In the previous problem, we have been given a value of a, and we have to calculate the corresponding probability. So this usually called as inverse problem, in which the probability is given and you have to find the particular value of the random variable corresponding to that probability. So what I can do is, we have to do it manually. We can do it in the Minitab as well. So first transform this x variable into z variable. Here I have no knowledge of x is unknown here, a, and mean and standard deviations are given. So here I can transform this by multiplying z with 6.8 and adding this. I will be able to get the value of a, and as I know this z value for area under the curve of 90, so using this cumulative distribution table corresponding to the table, I need to work out the corresponding value of z. So previously we have the value of z is given. I calculated the area under the curve. Here corresponding to the area under the curve 0.9. So you have to look into the table 0.9, and then you have to look into where your area under the curve would be covering 90% area. Then the corresponding value of z comes out to be 1.28. So if you look back to the different tables, one can see here 1.28 something here, 89.9. So 89 and 90. So the area would be between 89.9 is approximately 90% area, and it is slightly higher than 90.14%. So I just take the value of 1.28, the corresponding value of z, then area would be approximately 90%. So this is how we have calculated this z value, and once I know the value of z, I can easily find out the value of a. So the value of a comes out to be 170.904 centimeter. So area under the curve would be 90%, so corresponding value of x would be 170.904. So and the same problem can be done in Minitab as well. We have done it using the cumulative distribution table. Okay, the one more thing we can do is we have already seen that in binomial distribution, when your number of trials where your probability of success is order of 0.5, then your distribution is even though binomial is a discrete distribution, but the shape of the distribution would look like a symmetric distribution. What we can do is, as normal distribution is a continuous random variable and binomial distribution is dealing with a discrete random variable, so we have learned that at probability, when your probability is 0.5, then your distribution is like a symmetric distribution, and when your value of other than 0.5, whether it's smaller than 0.5 or greater than 0.5, then this is an asymmetric distribution. So or there is some skewness present in the distribution. What we do is we can approximate given distribution as normal approximation for any discrete random binomial random variable into normal random continuous random variable if your binomial distribution is such that where number of trials times the probability of success is number greater than 10 and the product of n and 1 minus p, which is the probability of failure times n. If these two conditions are satisfied, then one can use a normal distribution to calculate the probability of a binomial distribution. And let's say we see here, let's say we have a normal distribution which is a continuous random variable with mean, mu and variance. If we are dealing with a binomial distribution, we have a discrete random variable x here which is binomially distributed and parameters are number of trials and probability of success p. So we can make an approximation because once we need to calculate probability using normal distribution, we need a parameter mean and variance. In binomial distribution, as you know, the parameters are number of trials and probability of success, but we know how to calculate the mean of the binomial distribution, which is n times p, and variance is the product of n times p times q. Q is 1 minus p here. So we just approximate, let's say x become a random variable and which is binomially distributed where number of trials are 75 and probability of success is 0.6. So we can easily calculate the mean value of the random variable. Mean value would be n times p, 75 into 0.6, so 45 would be the mean value and the variance would be 18. So I can say that if I have to calculate if x is a binomial random variable and I want the probability greater than and equal to 52. So what I do is obviously x is a random variable and I'm using a binomial normal distribution to calculate the probability, where x is a normal random variable with corresponding mean is 45, which is an approximation of a binomial distribution, and its variance is 18, so standard deviation would be square root of an 18. So corresponding value of z comes out to be 1.65. So corresponding to z 1.65 greater than 1.65, I got this area. So from the table you will get the value of z greater than 1.65 would be 1 minus the probability z less than 1.65. So 1 minus 0.004948 would be the value of the probability we will get from the table. So we will be able to calculate this probability, and probability comes out to be 0.0495. Let's say if we try to, instead of solving, we are getting the probability of around 4.95%, around 5% is the probability. If we are approximating a binomial random variable as a continuous random variable. Initially we have been given a binomial distribution, so what I have done is I have calculated the probability using a normal distribution, and in normal distribution you need a parameter mean and variance, and mean and variance you calculated from the formula of mean and variance of binomial distribution, and once you substitute it you will be able to calculate that area under the curve of our from normal distribution. Let's say if we do it with instead of doing with normal distribution, if we do it with a binomial distribution, then we can see that from this binomial distribution table the probability comes out to be, when your number of trials are 75 and probability of success is 0.6, so the area under the curve is 0.0611. So you see for x greater than 52 the area is 0.061, which is around 6%. So earlier we got around 5%. When x is assumed as a normal random variable. So there is a difference, and the reason for this difference is because once we say binomial random variable, which is a discrete random variable, and in this case area under the curve is represented by these different bars, and this curve is not a continuous curve. So once we transformed put an overlapping of the binomial distribution along with the normal distribution, so we can see here that once it is a normal distribution, then it is a continuous curve, and area under the continuous curve is representing this probability. So once we get it from a normal distribution, so we get that area. But in binomial distribution, the area is represented by the rectangles. So area represented by that rectangle, and the difference in value, which 6% or 5%, is only because of the area under the curve in two different types of distributions. So there is a technique, we call it a continuity correction, by which we can improve our approximation for using that normal distribution to calculate binomial distribution. We already have learned a fact that the formula for binomial distribution is when your number of trials are finite. But as far as normal distribution is concerned, where there is no such thing as a finite number of trials. So if n is a large number, and np is greater than or equal to 10, and n times 1 minus p is greater than 10, then binomial distribution can be calculated using a normal distribution. And further correction in the value can be done by introducing an correction called continuity correction. And continuity correction is, let's say if your x is the value of your discrete random variable, and if you have to convert it into a continuous variable using normal distribution, for a particular value of c, you can say something 0.5 is subtracted and 0.5 is added. So once you are dealing with continuous, so you are dealing with some intervals. So if x is a discrete random variable, you are dealing less than c, then less than c means c plus some 0.5 value. And if it is greater than c, then c would be c minus some 0.5 value. Let's say for the particular previous problem where probability have to calculate for value greater than equal to 52. So what I do is x is greater than equal to 52 means x should be greater than 52 minus 0.5. 52 minus 0.5 would be 51.5. So instead of using x value 52, I am going to use the value of x would be 51.5 after performing the correction using this table. So my corresponding value of z would not be the earlier value, but it is a different value with the same mean and the standard deviation. So corresponding value of z comes out to be 1.532. So calculating the probability for 0.532 is 0.067. 0.063, which is somewhat closer to the exact value. So due to this continuity correction, we will be able to approximate the discrete random variable value of a discrete random variable can be calculated using a continuous random variable that is represented by a normal distribution. And with this continuity correction, your random variable, instead of calculating 52, we calculate 51.5. If your value is less than c, then the value of 52 would become, if x is less than 52, then it would be 52 plus 0.5. So we need to calculate from 52.5. Then this result would be close to that exact value. So this is how the continuity correction can be used to improve the approximation.